Hi, my name is Drew Griffiths, and this is my presentation for Physics 2212, Lab 6, Magnetic Braking with Faraday. So the purpose of this lab is to study the movement of a magnet falling through a conductive tube. We're going to collect data of a magnet falling through a tube of aluminum foil, and then model the system using ClosScript, and compare the results from the real-world system to the ClosScript model, and then draw conclusions. Observations we made / a preview: the magnet falls slower through the tube than it does through air without the surrounding conductive tube, and the average time for the magnet falling through the tube is 0.734 seconds. And with a magnetic dipole of 1.4875, the predicted time from the ClosScript model is 0.432 seconds. And then when we use a magnetic dipole moment of 2.173, the predicted time matches the observed time that we had in our real-world example. Six concepts and assumptions that we had for this lab is Faraday's law, which relates the induced electric field and the length of the closed area to magnetic flux. Then the magnetic flux is the magnetic field passing through an area, and the electric field is produced by the change in magnetic flux that follows the loop and is in the same direction as the current. This is part 2 of the physics concepts. We have the magnetic force, which is equal to the cross product of the current multiplied by the length vector and the magnetic field. And you can substitute in 2 pi r for L because this is a loop. And then Newton's third law, forces between two bodies are equal and opposite in magnitude. And then Ohm's law, current equals potential difference divided by resistance. And potential difference in this lab is the negative derivative of magnetic flux. And here are the system and surroundings and the experiment of the lab. The system is the falling magnet. The surroundings is the aluminum foil tube and the rest of the Earth. And the experiment is to drop a magnet through the conductive tube and observing the time it takes to pass through the tube. And the forces acting on the magnet are the force from the tube and the force of gravity. And air resistance is negligible in this lab. And during the experiment, we determined which pole of the magnet is north using the magnetometer app on our phone. And then record the mass of the magnet, determine the width, inner radius, and length of aluminum tube, drop the magnet through the tube several times, and record the time it takes the magnet to fall through the tube, and then average these times and model the system in ClosScript, and then we're going to compare it to the ClosScript to the real model, like I mentioned earlier. Here are the observed results and initial conditions that we found for this lab. So on the left here are the trials for each of our times, and the average time is 0.734 seconds. And on the right here, we have the initial conditions of the tube and the magnet. And here is my ClosScript code, which sets up the geometry of the tube, the properties of the magnet, calculating the magnetic field, and calculating the flux over dt through each ring due to the falling magnet. Here's more of my code. I'm sorry, the pictures are a bit blurry. I can fix that, but here's the rest of it. Here are the model results for the 2 different dipole moments that we tested in this lab. So the first one, the results differ between the computational and real-world model, and on the second one, the dipole moment of 2.173, then the time it takes to fall is equal to the one we found in the real-world model. Then discussion / sources of error. When the magnetic dipole moment was lab 3 was used, the predicted time was smaller. When we used the dipole moment of 2.173, like I mentioned earlier, then it matched the fall time from the real world example. And then some sources of error would be contact and friction, air resistance, and then timing errors, such as when we were recording the drop of the magnet. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? So nearly 0 resistivity would mean nearly 0 resistance. The induced current would be much greater according to Ohm's law, and there would be a larger magnetic force, and then the magnet would take more time to fall through the loop. And then what if holes or slots were cut in the tube? It would interfere with the rings necessary for current flow, and the reduction in current flow would reduce the magnetic field and decrease the time it takes the magnet to fall through the tube. In conclusion, when a dipole falls through a conductive body, there's an induced current that creates a force opposing the motion of the dipole, and thus the dipole moves slower as it falls to the body. And that's it. Thank you for watching.